All right, good morning, everybody. I hope you're having a great week so far. Um, can somebody confirm that they can hear me with just a thumbs up in the participant or a yes or perfect. Thank you so much. Great. Appreciate that. Okay, good. So before we get going this morning with our discussion about chapter 24, um, just a couple quick announcements. You should have seen the schedule for this week. We're going to be covering chapter 24. So your pre-lecture should have been completed by last night, along with your chapter 23 homework. So we'll meet Wednesday, Thursday, and Friday this week for Zoom sessions. Um, and then also another announcement you should have seen posted on Blackboard is that I've been getting a lot of questions about what to do if you're unable to make one of the live lectures, since I'm keeping attendance for that. And I posted instructions on how to handle that in the announcement. Essentially, if you give me some advance notice or some notice and we agree that that's reasonable for you to miss that live lecture, then you can go ahead and watch the recorded version and complete a really brief recap assignment for that particular lecture and get the credit for attendance back if you want to do that. So hopefully that's a good compromise. That's not supposed to be a mechanism to um, have you guys avoid coming to live lecture. I think it's important for everyone to come here and be able to interact with me and have questions, but this is an accommodation I'll make on a case-by-case basis. Are there any questions about that? I know a few people have already pinged me about different times during the semester where they might need to use that mechanism. So do let me know in advance, and we can approve that. Okay, great. So why don't we jump into the lecture for this week, or the material for this week? And so let me get my sharing going here. Okay, great. You should be seeing my iPad screen now. Let me bring back my participant and chat list. Okay, great. So we're going to be exploring chapter 24 this week. And this is all about what's known as Gauss's law. And it's really just this one concept that's presented in this chapter. This is one of the four fundamental equations that describe electromagnetism. And we're going to establish the other three as we go along this semester. And by the end of this, this semester, we'll have collected what's called Maxwell's equations, which are sort of the complete and sort of most compact description of how charged particles interact with electric and magnetic fields. And this is the first one we're seeing here. This Gauss's law, right, has some things that we've seen before, right? It has this charge term sitting here, and it has the electric field. So somehow this is an equation that very compactly and in a nice mathematical way relates how the electric field is tied to the charge in a really general way. And what you can see is that this, right, so this is just on the right-hand side, far right-hand side of this equation, it's just something that goes like the electric charge inside of some enclosed surface volume, right, inside of it, some enclosed surface, times our fundamental constant epsilon naught. And on the left-hand side is this funny integral, right? It's the electric field vector dotted into some area vector and then integrated over a closed surface. Okay. And we're going to explore this relationship this week. So we're going to see several examples of how to use this relationship from Gauss's law to rediscover the electric fields coming from certain charge configurations that we already solved using the superposition principle before. and as well as using it to extend our understanding of these fields. Okay. So in order to really make progress on understanding Gauss's law, the tough part for most students is understanding how to tackle this funny integral, this surface integral that you see on the left-hand side. You may not have integrated something like this before. And this quantity here that we see that's E dot dA, we're going to see that that's a flux. Okay, this thing is a flux. This tells me how much electric field is going through some small cross-sectional area that's related to some geometry that I define in the problem. And right, there's a dot product between these two things, and we're going to see where that comes from. So today what we're going to do primarily is to try to set the ground for solving these integrals. So we're going to talk about symmetries, and we're going to talk about flux in general today. That's what I'm hoping to accomplish by the end of the hour. And then tomorrow and Friday, we should be set up to tackle some problems using Gauss's law formally here. Okay, so that's the game plan. So symmetry. Let's start with a quick discussion about symmetry. And this is nothing fundamental to Gauss's law here, but if we exploit symmetries that we see in some system, we're going to find that it makes calculating that surface integral that we just saw on the previous slide much simpler. Okay. So I'm going to turn off the sharing momentarily so you guys can just see me. So here's the idea. We want to think about charges and the symmetries, right? And what do I mean by the symmetries? I mean, what are the operations that I can do on some system or some collection of charges that leave the system unchanged? And so let's look at a few examples. So here's a sheet of charge. So imagine that I have a bunch of positive charge spread out on a sheet like this. And so there's some symmetry that we could see. If I get this very close to the camera, if I shift this, so you can imagine this is almost like an infinite sheet of charge. If I shift it left or right or up and down, it essentially is unchanged. I still just have a sheet of charge everywhere. Okay. So there's some symmetry. I can shift that sheet in different directions and it leaves my system unchanged. Right? I can have other different geometries of charges, right? I could have a cylinder of charge, something like this. I just have rolled up charge. And right, this also has some symmetry. If I take this cylinder of charge and I just flip it by 180 degrees, I get back a system that's, or right, an object that's indistinguishable from my original object. If I rotate it, right, if I rotate it, it's also indistinguishable from, right, in any rotational, right, as I change the angle, I have a rod that's indistinguishable from the way it was to start. Okay. But if I rotate it in this sense, right, now something's starting to change. I can see that the configuration looks different relative to the way I'm observing it, that there's some shift in the distribution. Okay, so there's a symmetry about this rotation. There's a symmetry about, right, mirrorings across different planes for this particular cylindrical charged object. And I could also think about something like a charged sphere. So here I've wrapped a ball in my charge paper here, right? And if it wasn't wrinkly, you could imagine that as I rotate this thing in any direction, it leaves me with an object that's indistinguishable from the original object. Okay, but I do see this one, since it's localized in space, if I shift it left or right or up and down, well, clearly something's moving around relative to my position, right? I can see that shifting around. Unlike that infinite sheet of charge, when I shifted it, right, I couldn't really tell the difference of where I was on that infinite sheet of charge. Okay. So that's the idea of symmetries, right? We saw three different examples there: some planar symmetry, cylindrical symmetry, and also spherical symmetries just now. So here's the question, and the thing that's important to understand. How does the electric field, right? So if I have a charged object, say this sphere, what does the symmetry of the we know that these charges are going to generate an electric field because positive charged objects that are collected in space are going to generate an electric field in the space around that charged object. What kind of symmetry does that electric field have to have? Any ideas? What do people think? Well, let's play around with that concept. Radial symmetry. So let's go back to my cylinder here. What's the thing that's generating the electric field? Well, it's the charges, right? So here's what I'm going to do. I'm going to put a few different pins into this thing, and these are going to be representing my electric field here. Okay, so hopefully people can see that. Oh, okay. Let's see if I can get this to focus. Maybe, okay, there we go. So this pin, let me put a few in. I'm going to use it to imagine that those are some electric field lines that are coming off of this charged object. Okay. And I could imagine that there's one of these, right, charged field lines coming off in all of the, from all of the different charges that are applied in here. And here's the argument. So I'm just going to put 2 just for the sake of simplicity here. Okay. So here's my field lines. Again, let me get this to focus. Okay. These 2 pins are representing the field, right? Imagine that's a vector. The tip of my pin is an arrow that's pointing away from the cylinder, and the line is representing a field. Well, here's the argument we're going to make. Since the electric field is coming from the charges, it has to share the symmetries of the charges, right? Imagine that one of these electric fields was tipped to the side, something like that, so it had an angle. Well, that breaks the cylindrical symmetry of the field, right? Now, if I flip this object around, I can tell that the object has flipped because that electric field over here that's angled in a different direction points in a different way. So I can distinguish this geometry from this geometry. And the argument is that can't be the case because we can't distinguish the underlying charges. They look identical, right? The charges built up on that cylinder are indistinguishable. So I shouldn't be able to tell the difference from the fields, right? The fields should be identical because the symmetry of those charges is identical. And so that leaves me with only one choice for this particular system, that the fields have to be uniform, right? Have to also have cylindrical symmetry, right? If this thing points up, right? Imagine I have this pointing up and I rotate it around. Well, now that field at this point, right, there'd be another one over here. Let me add another field line just to make this symmetrical so we can see it, right? If they all 3 of these point upwards like this, then when I flip this rod, I maintain my symmetry. I can't tell the difference between this configuration and this configuration. And furthermore, I would have to have lots of pins pointing radially outwards so that when I rotate this thing, right, I would also have that the field is indistinguishable, just like the charges are indistinguishable, right? So the point is that the fields have to follow the symmetries from the charges because the fields generate, right, the charges generate the fields. And if I can't distinguish through some symmetry changes or rotations in the charges, I shouldn't be able to see that difference in the fields as well. So we can say the same thing for this ball here, right? I have to have field lines that are just pointing radially outwards away from this sphere, right? So that when I make rotations, I have an indistinguishable electric field from those rotations, right? If you imagine pins coming out in all directions, I could keep adding pins. And if I get the pins representing the electric field everywhere, if I just rotate that object, then the field is also indistinguishable, right? If one of these pins were to be tipped slightly sideways, right, coming off at some angle, then I could definitely tell, right, that there would be some particular point, right, on the field that would allow me to tell the difference between the rotational states of this charge sphere, right? So in that case, the not only is the charge spherically symmetrical, but the surrounding electric field has to be spherically symmetrical. And that's the same idea for the infinite sheet of charge, right? If I have an infinite sheet of charge set up here, okay? The idea is that my electric field has to be such that I can't, right? It can only point perpendicular to that plane because that's the only configuration I'll find where the field follows the symmetries, right? That is, as I shift the field, I don't get any changes in the positions, right? If I had a tipped electric field, I would be able to tell certainly about rotations, and I would break the planar symmetry. Okay, make sense? So the fields are going to follow the symmetries of the charges, and that's something that we're going to exploit as we try to understand Gauss's law. Any questions about that? Okay. Let me restart my sharing. Okay, good. So the other important thing that we're going to need to understand to make progress with Gauss's law is the idea of flux. What do we mean by flux? And your book defines this, right? So here's the idea of an electric flux. Okay, it's that if I define some area, okay, say some disk, right, in some region of space where there's an electric field. So you can see there's uniform electric field at that region of space pointing to the right. We're going to also define a vector that we're going to call the area vector. And it's just a vector that is perpendicular to my surface. And the magnitude of that vector is equal to the cross-sectional area of that window. Okay, so that's the visualization of that area vector in that diagram. This thing that we call the flux is just the dot product between that uniform electric field, or that electric field that is existing in that point in space, times that area vector, right? And this is a dot product, so we can write this like E, A, right? The magnitudes of these things times times cosine of the angle between them. Okay. We can just write this down. Okay. It's a dot product. So if that angle, right, is 0 degrees, we know cosine of 0, I just get back 1. That's when I have the maximum flux. Right? What does that look like? That's when this window is pointing in this direction. And if this thing is 90 degrees, that's when this window would be lying in this direction, right? So the flux, what is the flux telling you about? It's basically telling you how much field is going through your little window that you've defined, right? And flux is not something that we just talk about with electric field. It's a really general idea, right? You can define a, say, air flux or light flux or any kind of flux. It just counts, right, how much of some stuff is going through some cross-sectional area. So I don't know if you can still see my video, right? But if I have a little window, I'm showing you guys a little metal window on my screen here, right? I can think about the light that's passing through this thing on the way to the camera, and that's defined by some kind of flux. And you can imagine as I tip this thing, as I change the angle, you can see the size of that window that the light is passing through on the way to you is shrinking, and so less light is passing through my loop of wire. And if it's completely flat, now there's no light passing through the wire. Okay? That's the idea of this flux term. It's how much stuff is flowing through my little area that I defined in space. And the important thing about the flux is that it can be a real physical, well, it's a physical object, right? We're defining it physically, but this loop can be related to some physical object like this wire. I could ask you, what's the flux of, the electric field or the air flowing through this thing? But I don't need to have a physical object. I can just define in some coordinate system a window and talk about the flux through that sort of imaginary window that I'm setting up. And in this particular chapter, that's what we're going to frequently do. We're going to use this window, right? This area that we're going to draw is going to be some mathematical construct in a coordinate system that we pick, and we're going to calculate the flux going through that particular region. Now, we can think about some interesting relationships between the electric flux, right, and the charge. And here's a few points to keep in mind as we go along here. If I imagine making a closed surface, right? So here now I have a box, and so I have a different flux through each surface of the box. And in this particular example, you can see that the electric field everywhere points radially out, or out of the box, flowing out of the box. Well, if the total flux, right, there's a rule that says if the total flux for some closed surface, so if I have some region in space and it totally encloses the flux, or right, totally enclosed in my space, if the flux is positive, that indicates that I must have some, right, if the flux is flowing out of this thing, right? Remember, I would define some vector A that would point radially outwards from this thing. Okay, when we have a closed surface, we're going to typically define that area vector A so that it points out from the interior of the object. And you can see, since the A pointing out aligns with that electric field, I would get a positive flux. Well, what does that tell me about the charge? That tells me two things. One, it tells me that there must be some charge contained in this box because I have a positive electric field. And it also tells me that the net charge has to be positive. Okay. I can also see that the field lines through, right, that if I have no net flux in this lower example, I can see that I have field lines entering the box over here that would have a negative flux because I would have A pointing in this direction, and over here I have A pointing in this direction. So I would get a negative flux on the left side, a positive flux on the right side. Those two would cancel out, and I would get zero net flux. And that tells me fundamentally that there's no charge inside of that box. Okay, why is that? Let's just try to convince ourselves of that. Okay. If I imagine just, say, a positive charge, just let's think about a positive point charge here. And I can draw the flux, right, the electric field lines, right? So here's the electric field lines radiating off of this guy. All right, so there's the electric field. And now I can imagine drawing, right, a closed shape that I'm going to calculate the flux over. And let's say I pick sort of just like a sphere, and I don't have to have that charge centered, but I do something like this. And now what I'm going to do is I'm going to go around and I'm going to calculate the flux, right? So everywhere I have this vector A that points outwards. So you can see everywhere here, right, the A vector, because I'm defining it to point away from the interior of a closed shape. Everywhere that A vector is going to be aligned with my field, and I'm going to get a positive flux. Right here in this example, the flux is going to be greater than 0. And you can see I have a positive charge sitting in there. Well, what would happen if I picked a shape, say, a sphere over here? Well, now again, I would draw my area vectors A pointing outwards. And on the back side, let me carry these electric field lines through this object. And over here, my A would point, again, radially outwards. And you can see over here I have that my electric field vector is predominantly anti-aligned with my area vector, where over here it's dominantly aligned. So I get a negative contribution to the flux over here, and I get a positive contribution to the flux over here. And it turns out that those two are going to completely cancel each other out, right? Basically, if I have a field line that enters an object and then later exits that three-dimensional object, it's going to just leave me with zero flux, right? I had that same electric field enter and exit, so it doesn't contribute to the flux. And you can see that that's only going to happen if I have no charge sitting inside of this object. And if I had a negative charge, right? If I imagine that I had a negative charge, we know that the electric field there points radially inwards. Okay. And so if I enclosed that charge into a volume, you can see that the area vectors point away, the flux points inward, and when I calculate the flux over this whole object, I'm going to end up with a negative flux. Here my flux is going to be less than 0. So just by looking at the electric field and in some region in space, and if we draw a sort of a imaginary or just a construct of some coordinate system, a three-dimensional volume, and we integrate the flux over the surface area of that particular volume, we can know whether or not we have a positive or negative or any charge enclosed inside of that volume just by what the flux is. Okay. All right. Now, to calculate this surface integral that we see in Maxwell's equations, we're going to imagine, right, that we have some surface, and we're going to take that surface and we're going to break it up into tiny little flux windows that we're going to call dA. And again, everywhere that vector is going to point outwards from the interior if it's a closed shape that we're making. Okay. That A vector is going to point perpendicular to the surface here. And here's the important thing to notice here, that A vector, right, I can break the electric field up always into two components. I am going to be able to find a component of the electric field that's parallel to my A vector, and I'm going to be able to find a component of that electric field that's perpendicular to my A vector. And that's going to be an interesting way to break up the field, because if my electric field is perpendicular to my surface, then I'm going to get some flux generated. And if my electric field is parallel to my surface, then I get no flux, right? If I go back to my wire, I'm showing this on the video again here. If my flux is perpendicular, right, going in this direction, coming out of you, it can go through this loop and you get some flux. I imagine my fingers are the electric field. They're pointing perpendicular to the plane defined by this surface, and so they contribute to the flux. And if I tip the wire down like this, right, and have the electric field continue in this direction, it can never pass through that window, right? The flux lines, or the field lines, are parallel to that plane, and so they can never go through the plane. So when we make, right, so we're going to see tomorrow when we start solving some Gauss's law problems, when we see some collection of charge, and we want to try to draw some mathematical closed shape around it in order to calculate that flux surface integral in Gauss's law, we're going to try to pick, since it's free for us to pick whatever shape we want, it's just some imaginary shape that we're going to pick to try to use Gauss's law. We're going to try to pick a shape where the electric field is going to be perpendicular to the surface everywhere, because then this integral becomes much easier. This dot product, if I pick the electric field always parallel to A, then that dot product just becomes a regular multiplication, and I can just integrate over the surface. It simplifies this surface integral. Okay. So hopefully this will make more sense as we go through the problems over the next few days. Okay. So let's try to practice with just some simple examples to understand about electric flux. So here I have some window that I've defined over here. So this is going to be my area A. And I've got some electric field that's going to pass through that window. Okay. And I want to calculate the electric flux through that shaded surface. Okay, let's have you guys calculate the electric flux through that shaded surface. Let me go ahead and open up the poll. Which one tells me the electric flux through the shaded surface? Okay, good. Let's go ahead and end the poll. So most of you selected C. Let's see, how do we do that? Well, we know that the flux, let me get a better colored pen here. We know that that electric flux is equal to E dot A, or E A cosine theta. Well, what is this A vector? So in this particular example, the A vector is this vector that's perpendicular to my surface. And so it's pointing in the same direction as the electric field here. Okay. And so I'm going to get some, right, if I want to find, right, this thing, so I know that the angle between my electric field and my A is equal to 0. So this thing is just going to be 1. So the flux here should just be the strength of the electric field times that surface area that I have. Well, A here is just going to be 2 meters times 2 meters, 4 square meters, and the electric field strength is given to us, 100 newtons per coulomb. And so I just multiply those together, and I should get that the electric flux is just going to be 4 square meters times 100 newtons per coulomb, which should give me answer C here. 400 Newton meters squared per coulomb. Okay. All right, what about this one? What's the electric flux through this configuration? So I've laid that sheet down flat in this example here. Okay, I'm going to stop the poll. Most of you selected A, which is the correct answer, 0 here. So this is supposed to look like the electric field lines are parallel to the surface of a sheet here. And so they will pass over the surface, but I can never get an electric field line, right, penetrating through that window or making its way through that window here, right? All the electric field lines will just pass over each other. If I write down, in this case, the A vector is going to point in this direction, right? And so the angle between the A vector and the electric field is going to be 90 degrees. Okay. And so when I calculate my electric flux, that's E dot A, I'm going to get that this is equal to 0 because they're perpendicular to one another. Okay. Let's do this one. So now I have tipped that sheet up about 20 degrees with respect to the field lines. Okay, so notice that the angle here is showing me how that plane that used to be right parallel to the field lines is now tipped up at a 20-degree angle. Let's have you calculate the electric field in this, or sorry, the electric flux in this configuration. Okay, good. Let me end the poll. Okay, we have some split between B and C here. So let's see what the correct one is. Well, let me define that vector A, right? So again, flux is going to be E dotted into my area vector. How's that area vector going to point? It's going to point perpendicular to this surface, so it points in this direction, something like this. And now here comes the electric field. The electric field is this vector that points in this direction, E. Okay. So what's the angle, right? So in this dot product here, right, this is EA cos theta, where theta is the angle between, right, the angle between A and E. So what's the angle between A and E here? Well, it's this angle. Okay, it's this angle. What angle is that? Is that 20 or 70? What do people think? Yeah, 70. That's our 70-degree angle here. So that's the angle that has to go into the dot product expression to calculate the flux through that area. Okay. Right? That should be, right? So you should think about, right, the larger the angle, the smaller the flux, right? The way we're defining the angle. The larger the angle between the two, the smaller the flux. And right, the way that we define this angle, right, if this angle is 0, that means I have the maximum, right, distance between, right, I have a 90-degree angle between A and E. So it's important when you're solving these problems to always take that angle as the angle between your area vector and your electric field vector, and not, right, just whatever the the angle of the geometrical setup that's given to you. So really check and make sure that you find those two vectors that are in that dot product for the flux and find that angle between them. Okay, great. Okay, so this is an example from your book. And so you can look at this one after class. And so I'm just going to point out that we can solve problems like this now with this idea of flux. We could imagine having we could imagine having a parallel plate capacitor, right? Two parallel plates that have some charge built up on them. They're spaced apart by 2 centimeters. They're each charged to 5 nanocoulombs. One side is positive, one side is negative. And then what I'm going to do is imagine placing a 1 centimeter by 1 centimeter surface between the electrodes that's tilted so that its normal makes a 45-degree angle with the electric field. And then I could ask you a question like, what's the electric field through this surface? Okay. Well, the key here is going to be to make a diagram, right? So that we can understand what's going on here. I know I want to calculate this electric flux, so I need to define the area. I need that the field can go through, and I need to understand what the field looks like. Okay, and what does it look like? We know that for a parallel plate capacitor, I'm going to have a uniform electric field. I'm going to have a uniform electric field that goes between the two plates, right? So I could imagine drawing my two plates here. I have a positively charged plate and a negatively charged plate, and I have this uniform electric field that goes between them. What's the strength of that uniform electric field in this example? Well, we could look back to last chapter, and we know since this is a parallel plate capacitor, it has to go like the surface charge density divided by epsilon naught. That's something that we saw in the last chapter. So we can use the electric fields that we established in previous chapters. And they told us that this flux window is going to be angled at 45 degrees. This is right, they said that we're going to be using a rectangular window, so I could imagine changing this geometry that was 2 by 2. Right? And that's it. Now I have all the pieces I need to do this calculation. I can calculate the electric field. right? I can calculate the surface charge density by taking the charge that was loaded on the plates divided by the area of the plates. Those were things given to me in the problem. And then once I have that, I can just take the dot product of the electric field and that area vector. Okay, what is it going to look like? Here's my electric field that I calculate just from using the parallel plate capacitor formula. Here's the area that I calculate by multiplying the two sides of the surface that they defined in the problem. And then I have a cosine 45-degree term to take into account the angle. Okay. All right. What about this example here? So in this example, I have a positive charge generating a electric field, and the field lines are visualized with these vectors that are shown. And now I've drawn two different surfaces, two different windows that I want to ask about the electric flux through the windows. Okay. Which one has the larger electric flux? Which window is experiencing the larger electric flux? A, B, are they the same, or do we not know? Let's see what you guys think. Okay, I'm going to go ahead and end the poll. So we have a pretty good split between A, surface A has more flux, and C, the fluxes are equal. What do people think? Maybe we should discuss this one. Is there anybody that selected C, that the fluxes are equal, that could explain why they think the fluxes are equal? Anybody willing to? Or is there anybody for selection A that wants to defend that one? Yeah, hi. Is it Jihad?
Yeah, that's me. I mean, I chose surface A because I felt that the electric field had more dense field lines at surface A, which would have meant over the same area, assuming A and B have the same area, which they do, then I would say that A must have more flux. So that's why I chose it.
Okay, great. Thank you very much for sharing. Okay. There's some responses coming in on the chat. One, Aaron is saying, I initially put C because I thought the radius didn't matter. Well, now he's thinking A now because I think there's more E going through it. Emmanuel says, wouldn't the electric field at A be stronger? Noah's saying they would only be the same if the field was uniform. At least that was my reasoning. Okay. And Jacob's saying, since A is closer to the charge, the field should be stronger, thus increasing the flux at A. Okay, so I think you guys are on to the right ingredients, right? Remember, the flux is equal to E dot A. It depends on two things, right? It depends on the size of the window, right? First of all, the orientations of the window, that's the dot product, but also the size of that flux window and the strength of the electric field, right? So in this case, A, the magnitude of A is the same in both cases, right? They have the same cross-sectional area. But is the field strength the same for A and B? Well, the answer is no, right? We know as I get closer to the charged particle that the field strength is growing, right? The field falls off like 1 over r squared. The further I get away, the field strength is shrinking. And remember, that's visualized in these electric field lines by the spacing of the field lines, right? Remember, more pactly tight lines mean that the electric field is stronger in that region in space. And the nice thing about electric field lines then is I can, right, remember if I draw these electric field lines, right, they're just these vectors and the spacing indicates the strength. Well, the quick way with this graphical representation that I can understand the electric flux is to just count electric field lines that go through my fixed surface. So here you can see that I have these 5 field lines that make it through surface B, but I have these extra 4 field lines that, right, and all those field lines also pass through A, but there are 4 additional field lines that pass through A. So there's more electric field passing through surface A. They have the same, right, surfaces A and B have the same surface area A. And so that means that surface A has to be the one with more flux passing through it. Right? If I wanted to catch those extra field lines, right, if I wanted to have the same flux passing through surface B, right, I would have to draw it very large. It would have to capture all those exactly those same electric field lines that pass through A. And that's just showing this effect that the electric field is not constant in this particular example. It's changing as I go radially away from that positive charge. Okay. Okay, what about this example? I have 2 surface areas defined here, A and B, that you can see on the diagram. And they're both sitting in the same electric field, this uniform electric field, in this case, that points to the right, that's 100 newtons per coulomb. Which surface area, or which surface A or B has the larger electric flux? What do you guys think? Okay, let's go ahead and end the poll. So a fairly uniform split between A, B, and C here. Let's see if we can reason through what's happening here. Well, A, right, so let's imagine that I have this. Let's just label the sides. Let's call this B and this side C, and this length here, we're going to call that D. Okay. So we know that surface area A, right? No, sorry, let me change that. We know that area A is going to just be like B times C. And so the flux through area A, we see that that surface is perpendicular, or yeah, the surface is perpendicular to the field. So we know that the flux through this thing is just going to be like my 100 newtons per coulomb times B times C, right? It's just going to be the field strength times that area here. What's the area of surface B? Well, the area of surface B is going to be B times D. Okay. But let's see, can we relate that to A? So let's imagine that there's some angle that we're going to call theta here. Okay. And I can also now imagine that I can define, right, this surface vector A that points perpendicular to my surface. The electric field is going to be going in this direction, and so I'm going to want this angle here, right? This angle here is going to be 90 degrees minus that angle theta. Okay. And right, so when I calculate the flux through B, it's going to look something like my 100 newtons per coulomb, B times D, but then I'm going to have cosine of 90 minus theta. And you can check the geometry on this, but cosine of 90 minus theta is exactly right. That's this angle here, right? This is also 90 minus theta. And you can see cosine of 90 minus theta times D then is exactly equal to C. So this is just equal to 100 Newton coulombs B times C, which is identical to what I had for flux A. The two fluxes are equal. And I can also just visualize that from the field lines, right? Since these lines are perpendicular to surface A, any field line that passes through, right, surface A has to pass through surface B. And there is no electric field line that you can find that passes through surface area A or B and not the other one. So all of the same field lines are passing through those two surfaces. That means their flux, their electric flux has to be identical. Okay. All right, we're out of time for today. We'll do a few more quick flux problems when we get together for lecture tomorrow, and then we'll start working on some Gauss's equation problems. We'll use Gauss's law to understand electric field using these concepts. Okay, great. Thanks everybody so much. I'll hang around for another few minutes if you have any last questions that you want me to answer before you sign off for today.
Excuse me, can you please go back to show your work for this last problem we did?
Yep.
Okay, thank you.
Yeah, so the key thing here is that, right, if we define this as angle theta, then on this right triangle that you see here, this is 90 minus theta, which is exactly the angle that goes into the dot product formula. And so you can see that C is the side adjacent to that angle, and the hypotenuse is D. So D times cosine 90 minus theta is the same thing as C. Guys, I'm really sorry that my handwriting looks like a kindergartner on this PowerPoint thing. It really does a bad job with the Apple Pencil. I'm working on it. Hopefully it's tolerable for now.
Okay, I understand it now. Thank you.
Okay, you're welcome.